Welcome to Athena Astronomy, your gateway to the cosmos. Whether you're a stargazing novice or an experienced astronomer, this is your home for exploring the mysteries of the universe. Join us as we traverse the stars and unlock the secrets of galaxies, black holes, and everything within. I'm your host, Athena, ready to guide you on this celestial journey. So look up and let your mind wander into the infinite. It's time to discover the wonders of astronomy. Let's start with the interstellar medium in galaxies such as the Milky Way. These galaxies are made up of gas, dust, and cosmic rays. So let's start with the gas. Mostly hydrogen, 70% by mass, and helium, 28%, with trace amounts of heavier elements such as carbon, nitrogen, and oxygen. This gas exists in different forms, including clouds, where stars are born, and ionized regions around hot stars, crucial for various astrophysical processes. Dust. It makes about 1% of the ISM's mass and is composed of small solid particles like carbon, silicon, and sometimes ice-covered elements. Dust plays a vital role in absorbing and blocking ultraviolet light, which protects the integrity of the clouds and aids in the complex chemistry of the ISM. Cosmic rays comprise high-energy particles that travel near the speed of light, originating from events like the supernova. They are important for ionizing parts of the ISM and influencing both the chemical reactions and thermal properties of the medium. Star-forming versus non-star-forming clouds. Star-forming clouds are characterized by high density and low temperature. These clouds can collapse under their own gravity, overcoming internal thermal pressure to form stars. These regions are typically rich in hydrogen. Non-star forming clouds. Generally, these clouds lack the necessary density or are too hot, allowing internal thermal pressures to prevent gravitational collapse. They may contribute indirectly to star formation under altered conditions. Let's talk about star formation and the protostar stages. The process of a star formation starts when the gravitational forces within a dense core of a molecular cloud overpower the thermal pressure. So what are the stages of the protostar? Well, the stages include initial collapse. A dense core forms around the cloud. Now it's the protostar development. As the core collapses, it heats up, forming a protostar at the center that continues to excrete material. Then, it's the stellar wind emergence. At a critical temperature and pressure, stellar winds emerge, clearing the surrounding material. Main sequence transition. The protostar evolves into a main sequence star when nuclear fusion of hydrogen begins at its core. Mass range of newborn stars. The mass of newborn stars varies widely from less than 1/12 of the Sun's mass to over 100 times the Sun's mass. The most massive stars can influence the dynamics of their host galaxies due to their intense radiation and powerful supernova explosions. Life stages of stars on the HR diagram. Low-mass stars. These include stages from main sequence to the red giant, the horizontal branch, the giant branch, and finally to the planetary nebula and white dwarf phases. Each stage corresponds to specific changes in the star's core processes and its position on the HR diagram. High-mass stars. These stars quickly move from the main sequence to the red supergiant phase. often leading to a supernova explosion. The final stage might be a neutron star or a black hole, depending on the initial mass of the star. White dwarf characteristics. Stability. Supported by electron pressure, white dwarfs are the remnants of low-mass stars that have shed their outer layers. The limit. This theoretical limit defines the maximum mass for a white dwarf to support itself against gravitational collapse. Mass-size relationship. An increase in mass leads to a decrease in size due to the denser packing of electrons within the star. Types of supernova. Type 1 occur in our binary systems where a white dwarf accretes mass from a companion star, exceeding the limit and undergoing an explosion. Type 2 results from the core collapse of a high-mass star, marked by the expulsion of the star's outer layers and leaving behind a neutron star or a black hole. Neutron stars are extremely dense remnants of high-mass stars supported by the neutron degeneracy pressure. They exhibit strong magnetic fields and emit radiation as pulsaries. Black holes are defined as an event horizon. They represent regions of space-time where gravitational forces prevent anything, including light, from escaping. The singularity at the center represents a point of infinite density. So welcome and thank you for joining us on Athena Astronomy, a gateway to the cosmos. Join us as we traverse the stars and unlock secrets of galaxies, black holes, and everything within.